having given you all the tools about microevolution, macroevolution, and really worked through the evidence and explaining to you how these small incremental steps in evolution can lead to big change, now the kind of thing that we need to do is to set that aside for a minute and look at the origin of life. And this is perhaps one of the most controversial aspects of evolutionary biology. It is probably the kind of thing that most people have real difficulty with. And the reason for that is because science doesn't have all the answers. We have some really good ideas, we have some really good hypotheses, we can test a lot of these hypotheses, but sometimes they just fall short and a leap of faith may still be required. And so this idea of chemical evolution, the first part here in chapter 15, is where I'm going to start in on that. In order to understand how chemical evolution even works, one of the things we have to do is set a starting point. And the starting point clearly is the age of the Earth. So how do we know how old the Earth actually is? It says here the age of the Earth is 4.54 billion years, plus or minus 1%. Now, one of the things I want to point out to you is what this thing is, this plus or minus 1%. That is an error. And this is an admission that the kinds of research we do is never exactly perfect. It doesn't mean there is a question about how old the Earth is. It means that we can only be so accurate the further and further back in time we go. It is saying a little bit like if you're a stickler for things, you might say, in my bank account, I have $100.25. But most people would probably just say, I have about $100 in my bank account. It's kind of like saying that. Both of them are true, and it's just a matter of how accurate you want to be. And so this error gives us a sense of this. Now, what does that actually mean in years? Well, if you think about 1% of 4.54 billion years, that's 4,540 million years, right? That's what that is. And if you have 1% of that, then you take 2 zeros out, and so you end up with 45 million years or so. So the error that we're admitting is plus or minus 45 million years. Now that's already a lot of years. But compared with the entire length of how long the Earth has been, that's not that long. If you go back to the idea of a toilet paper roll, we had 400 sheets of toilet paper, and each sheet is about 10 million years. Well, that's 4.5 sheets of toilet paper. On a big, long roll, that's not that much, all things considered. Now, where do we get this figure? It turns out that we are now able to use not just a single approach, but we actually are able to use multiple approaches. One of these approaches is, of course, radiometric dating, but this time we're using two different isotopes. We're using uranium-235 and uranium-238, and as they decay, we're able to use radiometric dating of the appropriate age. This is something that happens over billions of years. Now, it turns out these elements, uranium-235 and 238, those are the kind of things we use in nuclear power generation. So these are not unfamiliar to us. They are things that we've studied for a long time, and we can be very accurate with these estimates. In addition, rather than just looking at this on Earth, people said, you know what? We don't just want to figure out what happened on Earth based on what we see on Earth. But if we can go to other parts of the solar system, namely the Moon and Mars, and we can determine that the numbers from Earth are reflected on these other celestial bodies, then we're really onto something. Because if the universe basically started at a certain time, and then our solar system formed pretty much simultaneously as the Earth formed, then we'd get these numbers from all these other places as well. And we do. So this is now very good. In addition, we can use something called helioseismic dating. And helioseismic dating is a little bit of a newer process. It's a newer process developed after radiometric dating. And what we can do with this is we can look at the ratio of helium and hydrogen in the sun. We can actually look at the sun and its radiation, and we can determine the ratio of helium and hydrogen, and knowing what we know about the reactions going on inside the sun, we can make a determination of how old certain parts of the solar system actually are. So there are multiple ways by which we can now determine this age, and we've narrowed it down to 4.54 billion years. One thing that's important to note is that when we're making these calculations aren't jumping around. So it's not like somebody says, oh, it must be 40 million years, and then it's 12 billion years, and 6 billion years, and 2 billion years. No, whenever you use these type of techniques, you end up with the same numbers, and these numbers have been refined and refined and refined over the last 50 years or so, and we're always getting closer and closer and closer to a single number that everybody agrees on. So there's no huge variation. This is as best as we can determine the age of the Earth. Now, if that is the age of the Earth, 4.54 billion years is a long time, no doubt about it. What can happen during this time? Well, if you consider the traditional approach that somebody might take to understanding evolution, then the story may go something like this. Well, life on Earth may have developed over time, but life on Earth is a unique thing that happened based on chance. And it is one of those things that is very rare. And it is a wonderful thing that happened, and everything had to be just perfect for life to form, and this is why we're here today. So it's a very unlikely thing. It's kind of like winning the lottery, but twice or 3 times or 4 times in a row. That's how unlikely life actually is. And so one of the things that we should do is try to figure out where life comes from, the way we know it today, and perhaps trying to see where some ideas may come from and how it may have originated. Now, we know for sure that today organisms arise only via biogenesis. Biogenesis means life from life. So if you have a cell, then you can make another cell. If you have a rock, you can't make any cells. That's biogenesis. And that is all in our research today we can see. There is not an instance that we have been able to determine where something non-living turns out something living. Just doesn't happen. So therefore, we end up with a paradox. This is now known as the biogenesis paradox. And the reason for this is, if life did originate from non-living materials, then we'd have to break through this idea of biogenesis. If all we see is that life comes from life, then how could we possibly ever get life from non-life? This is the conundrum, and there is no easy way around that. So what do? Well, you go back in the fossil record and you figure out, when do you actually see things that could be considered living? And there are some very simple prokaryotes, things like bacteria, that are in the fossil record of about 3.9 billion years ago. Prokaryotes, that's it. So clearly one of the things we can say is that the oldest life forms on Earth were very simple. And if we analyze this with our understanding of simple life forms today, we would say that they looked something like bacteria, probably without a cell wall, and probably composed of a few key chemicals, the macromolecules of life, and obviously some type of membrane surrounding them. So something very, very basic. And that's what we see. And based on these very basic kinds of organisms, we would then have to create a hypothesis by which we can get to those kinds of very primitive types of organisms via some series of evolutionary steps. And because before things are living organisms, all we have is chemicals, we would call that chemical evolution. So we would expect that, yes, there was organismal evolution, but there was a transition from chemical evolution to organismal evolution. And that transition, that is where we have to start our investigation. How do you get to make something that's just a bunch of chemicals into something that's an organism? And this is a very tricky thing because nobody was there to see it. So let's start with the kind of chemicals we think were there. Now think about the evolution of the solar system. If that's what you can conceive of, you would expect there to be a large amount of molten rock, and this molten rock separates into different planets, and it congeals into things like Mars and like Earth and like Venus and so on. Then what kind of chemicals could there be in such a situation? And in order to find out what could be there, you may look at molten rock, look at lava today, and see what's in it, perhaps. And you find that there are a variety of chemicals in the lava based on the fact that it comes from the inside of the Earth. It's not the kind of crust that you see up above, but you find that the following: water, methane, carbon monoxide, carbon dioxide, ammonia, hydrogen sulfide, and some kind of phosphate group are there, can be found. So you have a basic set of chemicals, and that may be your departure point for chemical evolution. So start with some very basic chemicals, and then put those chemicals together in various kind of mixtures and various kinds of vessels and various kinds of conditions and see what happens. So let's forget about the timeline. Let's forget about how likely it is or not. We just start with something. Let's take these chemicals, mix them up, and see what we can do with it. So that's the basic premise of starting some chemical reactions on the early Earth. And it turns out, and this is something that was surprising, that counter to some of the concepts of rare chemical evolution and unusual things having to take place, it is actually a fact that when you take those inorganic materials I just showed you, you place them together in any quantities, in any conditions, they actually will produce organic compounds. Now this is kind of weird, because why would the chemicals do that unless there is something about the nature of the chemistry itself that makes them want to combine with carbon? I mean, after all, that is what organic molecules are. So something about the energetics of all these inorganic molecules shows us that they prefer to be connected to carbon. Now, that is not something that you could immediately assess when you're looking at carbon monoxide, carbon dioxide, water, and so on. You wouldn't guess that they would come together, but then you wouldn't guess either that if you take sodium, a metal, and chlorine, a gas, and you put them together, you get a salt, right? This is one of those things that you just can't guess. You just have to try it out and see what you end up with. Well, of course, one of the things that has to happen is that you need to be able to have these chemicals interact with each other freely, have the electrons interact without anything that would draw away some of these electrons from them. And that is why you cannot have any oxygen in the atmosphere. As we learned in Chapter 6, oxygen is a very powerful electron magnet. It drove that whole process of cellular respiration so that the electrons would bounce all the way until they ended up with the oxygen. That's how powerful it is. And of course, the oxygen pulls away electrons from the metal in your cars and makes it rust. It pulls away some of the electrons from your skin and makes you age. All of those kind of things are what oxygen does. And so not having oxygen in the mix frees up the chemistry a little bit to do what it can do. Now, we know that there was a lot of volcanic activity, and that there was lightning, and there was seismic activity, and it was hot, and there was increased pressure, and there was all kinds of things, including ultraviolet radiation, that were external effects on this whole business. So when people first started this concept and work on this concept of chemical evolution, they thought, well, why don't I just work with something that I think was present on the early Earth? So I'm going to take these chemicals, I'm going to make myself a whole bunch of test tubes, and I'm going to put a variety of these chemicals in different combinations into these test tubes. I put some of them back in the fridge, and I'm going to use some of them in my little setup here. And the person who started doing this was Stanley Miller. He was a graduate student at the time, and he thought it would be a cool idea to try and recreate in the lab what the early Earth might have looked like in terms of the atmospheric conditions. And so he has a setup. There it is. There is Miller, and he's looking at his contraption, and you can see here there's a little bit of ultraviolet radiation going in, and there's a way to heat this stuff up, and it circulates as it bubbles over, and you can have the pressure change, and you can have some lightning strikes and all that kind of stuff. And if you do this, indeed you do get organic monomers. Pretty cool. In fact, it was newsworthy that this graduate student in the 1950s put together these very basic chemicals and came up with organic monomers. That was considered a great achievement in terms of showing that chemical evolution can happen. And it was. I mean, for Miller, it meant that he got a job at a good university. He was able to run his own research program. He became famous for having tried this experiment. And so famous that eventually, when he retired from his job, the Smithsonian came and said, Dr. Miller, can we have your contraption? Can we have your stuff? And he said, sure. And so this whole thing, this contraption, is now on display at the Smithsonian. And you know, you can just imagine this little graduate student behind his vial. It's just the way they showed in this picture. And so one of the things they did when he retired is they cleaned out his lab, and so the story goes, they looked at the freezer in the lab, and they found some of his old vials for when he did these experiments. And like I said, he tried all kinds of combinations and repeated these experiments umpteen times to be sure. And one of the things they found is some of his old little mixtures. And those mixtures had changed in what they looked like. People said, oh, well, these look different than what you started with, so I wonder what happened. Well, it turned out that even if you leave that stuff in the freezer for 25 years, it still produces organic monomers. Huh. Well, people picked that one up and said, well, let's see what else we can do. Maybe you don't have to run it through this contraption. Maybe you can do all kinds of other things and produce organic monomers doing that. And so they tried this by using impact shocks, by taking it to space, by doing it in really high temperature, in high pressure, in low pressure, in absolute zero, near the deep sea vents, without the deep sea vents. And whatever you do, however you allow these inorganic molecules to react, you can produce organic monomers. Now, this is interesting. 100% of the time, when you put these chemicals together and you allow them to interact under whatever conditions you can possibly imagine, they will eventually form organic molecules. And eventually meaning not even in a matter of years, but in a matter of a few weeks and months. So that step in chemical evolution that takes us from inorganic molecules to organic monomers does not appear to be rare at all. It's not even unusual, it is inevitable. That is what the chemistry of these molecules will do. Period. Well, that's news, of course. So, however it happens, it works. And it is now even possible that some of these molecules may have arrived not even from Earth itself, but from other parts of the solar system. So I'm very curious to learn what they're going to find when that probe lands on that comet that's coming up in the next couple of weeks or so. Because if they find any organic monomers on that, it's definitely a possibility that those kind of things, as they land on Earth, they bring with them some seed chemicals to start chemical evolution over again. So it's very interesting. Anyway, that's stage one. No big deal, really. And it can be done and achieved in the lab all the time. How about stage two? Once you have an organic monomer, you don't have the molecules of life yet. If you remember what we talked about when we discussed the molecules of life is we started with monomers, and then we had dimers, and then we had polymers, and we had to sort of piece them together. Remember? Glucose, 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 glucose. And when we put those together, we had something called dehydration synthesis. That was the key thing. And dehydration synthesis doesn't happen just willy-nilly. It needs some special conditions. But what kind of special conditions? Well, for example, sometimes it might need a little heat. Sometimes it might need some kind of molecule to help it along, some kind of catalyst perhaps. And it turns out when you look at some of these very simple organic monomers produced by the methods that we just discussed in stage 1, you can actually combine them by simply putting them on hot rocks or clay. Clay in particular is pretty cool because the silicate crystals in the clay not only are able to combine these molecules, but it can also assist making more of the same. So clay can actually launch replication of organic molecules. Now, if you have a random mixture of organic monomers, you can connect these. That's what the rocks or the clay can do. But if you're looking for a functioning macromolecule, what you want is something like glucose, 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 glucose. That's what you want. Or you want the right kind of amino acids put together. So you don't want a random mixture, but you want something that's perhaps more alike to get together. And it turns out that silicate crystals can do this. This is something about the chemistry of silicate and how it interacts with these organic monomers. This is another kind of chemical evolution that wasn't particularly well known, how the substrate, in this case silicate crystals, can help produce functional macromolecules. So one more time, we don't have a situation where you need some very rare kind of circumstances. All you need is silicate clay, which is basically what a lot of the planet at that time was made of. We can still find on this planet a lot of places with silicate clay. And you can end up with some very short but functioning macromolecules, things like RNA or polypeptides. Now, if you are looking at this from a chemical evolution perspective, then one of the things you might say is, well, which one of these came first? That's a chicken or the egg question. Do you start with the nucleic acid, which holds the information to make proteins? Or do you start with proteins, things like simple enzymes, which can help you build some of the nucleic acids? If you remember, you start with a nucleic acid, DNA, you have a protein, an enzyme called RNA polymerase that helps you make RNA, and that's how you basically end up making a protein, right? So you need proteins to make more proteins. So this chicken or the egg question isn't so easy to figure out. Well, if our track record up to this point is any indication, then it doesn't have to be a chicken or the egg question, but it could be a chicken and the egg question. Because if you can make a short RNA strand and you can make a simple polypeptide, why do you need to ask which one came first? Why don't you just say, okay, let's make them both and see what happens? And so let's make them both and see what happens means that you don't have to worry about which came first, but you simply start testing all possible combinations. And if you start testing all possible combinations, then once again you find that chemical evolution that moves towards RNA and polypeptides interacting with each other isn't something that is so unusual. It happens. People have done these kind of experiments over the last several years in the lab, and they find that there are multiple ways by which this can happen. Multiple different types of RNA strands, multiple simple polypeptides, they start to begin to interact with each other. It's almost as if there was some kind of natural selection already active in a way to pick the things that work better. But wait a minute, we're still in chemical evolution. Natural selection was something that was postulated for organismal evolution. So we're not quite there yet. but it appears as if even at the very basic chemical level, on the way to what some might say could be a living organism, we're already seeing that those things that work better together are somehow emerging from the morass of randomness. Things are actually starting to gel, if you will, with this business about polymerization. So the first two stages of chemical evolution I want to impress upon you are not particularly random. There's something deep in the chemistry of these molecules and atoms that makes them do certain things. And it's quite nifty to think about it that way. Now, the next two steps are relatively straightforward. One thing that conveys a clear advantage to any chemical system is if you have a reaction vessel that is separate from other chemicals. If you try to create an organic chemical in particular, what you do is you add the components and you have a reaction vessel, and then you let these components do their thing. You don't throw anything else in there. That is what gives you the best yield in organic chemistry. If you've already done some organic chemistry, then you'd recognize the term yield. In some organic reactions, if you don't do a very good job in keeping things separate, the yield is terrible. You try and do this reaction and it just doesn't work quite right. Well, if you give a molecular co-op consisting of something like RNA pieces and something like basic polypeptides as shown here, a reaction vessel that's a little flexible, like the phospholipids that surround our cells, then you can actually form a pre-cell. Now, if you have phospholipids, you throw them in some water and you shake them up, they will form these types of cells, these pre-cells, the phospholipids. That's just what they do. They form a bilayer, they form something like a membrane. That's just what these chemicals do. And if you put into that same solution with the phospholipids some basic organic molecules and you shake them up, then some of these pre-cells are actually going to enclose some of these organic molecules. So this again is not a very difficult reaction to deal with. You just need to do a lot of mixing, and of course with the time that we have available to do this, we can do a lot of mixing. So stage 3 isn't really that particular either. Now lastly, stage 4 would be to actually get molecules that self-replicate. Research over the last few years has shown that RNA is a very peculiar molecule. When people first started to investigate RNA, they understood that it was the kind of thing that carried information from the nucleus to make proteins. That's something we talked about in chapter 10. They understood that it was something that brought amino acids to the reaction. It was something that made ribosomes. But people subsequently realized there was a lot more RNA in our cells than could be accounted for by just all of those kinds of processes. And it turns out that rather than just producing the tools, the polypeptides, the proteins in our cells, RNA can also act as a tool itself. It can be a tool, and in that capacity we call it a ribozyme. Not a ribosome, but a ribozyme. And it's basically taking up the activity of an enzyme. So if you have something that's like a basic nucleic acid, something like a basic RNA, it can actually multiply itself. It can begin the process of self-replication. And this is one of the key things about living organisms. We have a built-in copying mechanism. We make more DNA, we make more RNA, we make more cells, right? All of that is built-in copying. So one of the main things that you have to achieve if you're going to build a functioning organism is some way to self-perpetuate the organism. And of course, if it's working well and if it's self-perpetuating, then it becomes subject to natural selection. And who knows where along this path of self-replication something that gives it the spark of life comes along. All these mechanisms are testable, and that's always a good thing. When you're working with something that's not just an idea and not just conjecture, but an actual testable hypothesis, then you're making big strides. The problem is that we still haven't been able to make that transition from chemical evolution to organismal evolution. So there's still something missing. We don't know what is the thing that creates that spark of life, and suddenly it runs away and it is a proper cell. We don't know what that is yet. People have been making various experiments. They start with something that's very basic and they put it all together and they try and sort of make it go, but we don't know how. So that transition is still very elusive, and for the time being, what I have decided to do for myself is simply make a leap of faith one way or another, and I think that this, what I've described to you here, is quite plausible. It is so plausible to me, in fact, that the question of multiple genesis arises. Given the way that chemical evolution leads us to this point, and repeatedly, and with ease, and with all the different permutations, then it is more likely to me that simple cells evolved more than once than not having them evolve at all. It is just so likely based on the fundamentals of the chemistry involved. Now, obviously, some of these life forms have become extinct. If it happens multiple times, we don't see dozens and dozens of different types of organisms. We only see a few. In fact, we're working right now with 3 domains. We have the prokaryotic cells, we have the archaea, and we have the eukarya. Those are the 3 domains. And perhaps they weren't off of the same block, not off the same tree. Maybe they came from different origins. Who knows? All we see today is that certainly amongst the archaeans, there's some very, very strange kinds of organisms with very strange phospholipids and with very strange cellular components. So strange that you wonder how they could possibly all be related. And so these unusual metabolic processes, they're sometimes so unusual that rather than trying to force them all into a single family tree of life, if you will, perhaps you should just leave them out and assume that maybe there were multiple origins. And if you take that to an extreme, then you might say that if the chemistry that we observe and are able to research on Earth is similar elsewhere in the universe, and there is no reason for us to believe that a periodic table of elements would be any different elsewhere in the universe than the way it is here, we would still end up with some type of organic chemistry that rules the roost, so to speak. We would end up with the same type of chemical evolution, the same type of options, the same types of life forms. Now, they're probably going to have a vastly different history than ours, and the reason for that is simply not all planets have meteors hitting them, and then 65 million years later you have something like humans evolve. So the history of each of those places could be fundamentally different, but the point is the life forms are probably still out there. In fact, if you believe the Drake equation, and that's a little bit of a stretch, it's a little controversial, doing the numbers and trying to impose some kind of probability scheme on chemical evolution and evolution in general, then one can estimate, given how many planets, livable planets, are there in the Milky Way, that's our galaxy alone, you should have somewhere out there at least 2 other extraterrestrial civilizations. But hey, the universe is a big place. We haven't found each other yet, and maybe we never will, because it is a vast expanse out there. But just the basic idea of chemical evolution should lead us to the understanding that, gosh, it's possible, and maybe we should say it's probable.